This is Unit 10.4 on testing two variances using the F-test. Now back in 8.5.2 we tested this hypothesis that the two means were the same. In other words, that mu1 minus mu2 is 0. No difference between the two means. Or mu1 equals mu2. And we did it with small samples, right? So we used a t-test. Now when we used that t-test, we had to decide if the variances of sigma 1 squared and sigma 2 squared were equal or not equal to. Well, we didn't really decide. We were just told in the example or the problems that assume the variances are equal or assume that they're not equal, and then we just went on with the problem. But now we're actually going to test that the variances of two populations are or are not equal. So let's just talk about this F distribution. The F distribution turns out to be a ratio, so a ratio, it's just a fraction, of two independent chi-square random variables, each having its own number of degrees of freedom. Here's a picture. So the two variables are both chi-square, so I'll draw a chi-square curve. This will be our F distribution. And it is a family of curves, so there's, different curves that you can get depending on the number of degrees of freedom. So maybe, for example, it's a ratio. So you have the degrees of freedom maybe for the numerator, and then you have degrees of freedom for the denominator. So maybe, I'm just making this up now. Maybe this one here is a 5 and this one is a 9. All right, so for different degrees of freedom, you get different curves, right? You get a different member of the family. And the curve, as you can see, is skewed to the right, right? It's skewed to the right. And it starts at 0, and it's because they're chi-squared, right? Chi-square over chi-square is going to be positive. So it starts at 0 and always moves out to the right. So always positive values. So to run a test on these two population variances, sigma 1 squared and sigma 2 squared, two things have to happen. First of all, the populations have to be independent of each other, meaning there's no relationship between one population and the other. And the second thing is that each population is normally distributed. So if you look at the variables in one, you get a normal distribution, and the variables in the other, you also get a normal distribution. Now, here's some notation we're going to use. And just to make things a little bit easier, we want to keep things positive. So how about if we do this? We'll have population 1, population 2, and we know the two populations are independent. Each population is normally distributed. And when we start writing up in problems, let's use the larger of the variances to be our population 1. So the smaller one will be from population 2. So we're going to assume here, I'll just put it here, when we designate which one's going to be which, let's say that S1 squared is going to be greater than S2 squared. And then in our notation here, we'll have N1 will be the sample size for the first population, sigma 1 squared the population variance for the first population, and then N2 sample size for the second population, sigma 2 squared the population variance for the second population. Just a matter of notation. Now when we set up our test, we're going to test that these two variances are equal. So we're going to test something like this. The sigma 1 squared minus sigma 2 squared is 0. That means there is what? There's no difference between the two variances. Or, if you like, maybe you could just write it like this. H naught states that sigma 1 squared equals sigma 2 squared, that the two variances are equal. And then we're going to write the alternate hypothesis like this. If we write this form right here, now remember what we're doing. We're just going to assume that the number 1 is the bigger number in our sample. All right, so what I'm going to write here then is that sigma 1 squared minus sigma 2 squared would be greater than 0, right? Because we're assuming that the S1 is bigger than the S2, right? So this is the bigger one here. In fact, let me put a 1 up here and a 2 up here. All right, so because 1 is always bigger than 2, we'll have a bigger number here minus a smaller number is going to be positive. Or we could just write, if I wrote it with this form over here, I would just say that, if I can get it to right here, I will say, yep, get it to right, sigma 1 squared is greater than sigma 2 squared. And here is the F statistic. It's the ratio of these two sample variances. So it's going to be S1 squared over S2 squared. All right, so once you have those sample variances, here's how you get the F statistic, the F star. And the degrees of freedom for the numerator is going to be N1 minus 1, that's sample size minus 1. And the degrees of freedom for the denominator, that's going to be N2, that's sample size minus 1. Let's do an example. This one's right out of the book, number 6 in 10.4. All right, so what's going on here? Two plots of Rothamsted Experimental Station. So two plots at this place here were studied for production of wheat straw. Now, for a random sample of years, the annual wheat straw in pounds from one plot was, okay, so here's the annual wheat production of one population, and here is another. Okay, so actually you can see what we have here. What have we got? In this case, oh, now they're telling us, use a calculator to verify. Okay, so we don't have to do that, and we don't have to do this one. We're given that one. Okay, so that's nice. But what do we have for N1, and what do we have for N2? Well, N1, 2, 4, 6, 8, 10, 11. All right, so N1 is 11 pieces of data, and N2, we've got 1, 2, 3, 4, 5, 6, 7, 8. 8 pieces of data. And what are they asking us down here? Test the claim that there is a difference either way. All right, so a not equal to test in the population variances of wheat straw production for these two plots, and use 0.05. Now I'm just going to decide which one's going to be population 1, which one will be population 2. Now just as a matter of ease, I'm going to choose population 1 to have the higher of the two variances. So when I look at this variance is 0.3. This one is 1 point. Okay, this one's bigger. So I'm going to let this be population 1 here, all right? So, but if I even write that, this would be population 1, and this is a smaller one. That'll be population 2. So population 1 will be this number here. That's going to be the S sub 1 squared is 1.078, and no, I just got that totally backwards, didn't I? Population 1 is the bigger one. That's going to be S1 squared will be the 1.078, and population 2, S sub 2 squared, that'll be the 0.318. Now, down here at the bottom, test the claim that there is a difference either way in the variances. So a difference either way, that's just a not equal. That's a two-tailed test. So how about if we set it up like this? H naught, null hypothesis, states that sigma 1 squared equal to sigma 2 squared. Alternate will be sigma 1 squared not equal to sigma 2 squared. Let's run this test on our calculator so that we can get the p-value. So on our calculator, here's where we're going to go. I'll do it over here on the left. You're going to go to Stat, of course. All right, and then you go over to Tests, of course. Now, you have to scroll down. It's probably easier to scroll up, but you go all the way down to item E, and E is a two-sample, it says two-samp F-test. All right, so go all the way down to E and select E. So when you select E, two-sample F-test, here's what comes up, asking us to input this information here. So first of all, the input. Are we inputting data, individual values from a list? No, we're putting in the summary statistics. So we're going to select this one. Now we need to determine what is our first population and what is the second. All right, this is why we chose up here, and it's just convenient to choose the bigger number to be population 1. the smaller number to be population 2. So S1 and N1, I'm going to go with this one here because that's the bigger number. But look, what they're asking here is for S1, that's the standard deviation. What are we given? We're given S squared. All right, so we need to get the square root of that. All right, so we don't just have S, but we can get it easily. On our calculator, just have the calculator compute it. So press second, X squared, right, all on the left side of your keyboard. So second, X squared, because on top of X squared is square root of X. All right, and then what you get when you do that is you get, it says, square root with the parentheses. So put in the 1.078 and then close the parentheses. You don't really have to. And then press enter. If you don't close the parentheses, the calculator will. All right, so here's what I got. When I did this, I'm going to write 1.038. 1.038. Okay, well, it doesn't matter. It's in the calculator already. Carried out quite a few places. Now, N1, that's this sample size. That is the sample size of our population 1, which is 8. All right, so let's put an 8 here. Now, what about S2? This is the standard deviation of our population 2. Now, population 2 is this one up here. Now, we're given the variance, right? We're given the variance, so we have to take the square root. So I'm going to do the same thing I did down here. I will press second, the X squared key, because on top of that is the square root key, all right? Square root, and then when you do that, you get a square root with a parentheses. So now put in the X squared, which is that 0.318. So type in 0.318, and then you can close it if you like, probably a good idea, right above the 9 key. And when I pressed enter, my calculator shows 0.5639 ... All right, N2. All right, so you press enter and then N2. What's our population size for the second population? That was our second population, 11. All right, so put 11 in here. And then let's select the alternate. Now, the alternate was, which one? We're doing just a difference. Is it the same or is it different? So we're going to select this one right here. So get your cursor over here, press enter. When I press enter, here's what I get. Calculator again reminds us of what our alternate is. Sigma 1 not equal to sigma 2. All right, now here's the F statistic. So this is F star. If we were doing this with the traditional approach, the critical region approach, looking things up in tables, we would get 3.39, say, 3.39, but we're not using that approach. We're using the p-value approach, and I'm getting 0.079, well, I'll round up here. How about this? Okay, that's going to be my p-value. Well, that's enough information we need. Let's run the test. So what are we going to do? We're going to compare p to alpha. All right, so a little table is the way I do it. So p is 0.0798, or about 0.8, right? This is about 8%. Alpha, now up here, alpha, okay, they've told us to use the 0.05 level of significance. So we're going to run this at 0.05, which is what, about 5%? Now, compare them. How does say about 8% compare to 5%? Well, 8% is bigger than 5%, and if it's bigger than, right, greater than, that tells us to, yeah, you got it, fail to reject H0. Now, let's just see what that tells us to do. We're failing to reject H0. Now, here's H0. H0 says that the two variances are equal. Well, we're failing to reject that. All right, so we don't have enough evidence to reject this. So let's write a conclusion. So let's write a conclusion. As we usually do, at alpha equals 0.05, we'll state our alpha value, how often we're willing to be wrong. So at alpha equals 0.05, this sample indicates there's not enough evidence to support a claim that the population variances are unequal, right? Here's that they're unequal. We're not going with that one. We don't have enough evidence for that, and we have to stick with this until we get maybe more evidence.